everyone, today we're going to talk about minerals again, the essential building blocks of our planet in our everyday life. Hello everyone to Geology 1A, Physical Geology at West Valley College. Today we're going to talk about minerals a little bit more. They are the building blocks of everyday life, whether it's graphite in our pencil, the salt on our dinner table, the metals in your phone or the gemstones in jewelry. Minerals are everywhere. And let's recap what is a mineral. A mineral is a naturally occurring, that means not made by people, a combination of specific elements following a pretty specific chemical formula and arranged in a repeating three-dimensional structure, what geologists call a crystal lattice. So if you grow a diamond in a lab, it is still a mineral if it also occurs naturally. But something made only in the lab, that's not a mineral. Most minerals have pretty rigid chemical recipes. For example, pyrite is always FeS2, 1 iron, 2 sulfur. That said, some minerals allow for variability. For instance, olivine can be FeMg2SiO4, meaning iron, Fe and magnesium can be present in any proportion. But the structure matters most. Volcanic glass and opal have a lot in common with minerals, but their internal structure doesn't repeat regularly. So they're not true minerals. 2. Atoms. Atoms are building blocks of minerals. All matter, including mineral crystals, are made up of atoms. Now, atoms have protons, that is the positive, in the nucleus, neutrons, the neutral ones, also in the nucleus, and electrons, the negative charge, orbiting outside the nucleus. So you have your nucleus and then you have your protons and neutrons, and then you have your electrons. The number of protons is the atomic number, what makes each element unique. For example, hydrogen has 1, helium has 2. For heavier elements, the number of neutrons is often higher than protons, helping stick lots of protons together despite their natural repulsion. Electrons whirl around the nucleus in shells or energy levels. The outermost shell holds the key to how atoms bond, because every atom seeks a full outer shell, often 8 electrons, the Euclid rule. How atoms bond, the basis for mineral structures. At the root of the mineral formation is chemical bonding. Let's see two main types. One is ionic bond and the second one is covalent bond. Now, ionic bond. One atom donates an electron, another receives, creating positive and negative ions that stick together. A classic example is halite, which is NaCl. Sodium loses electron, becomes positive. Chlorine gains 1, becomes negative, and opposites attract. Okay, so that's your salt, sodium chloride. Now let's go to covalent bonds. Here atoms share electrons. Diamond is a classic. Each carbon atom bonds with 4 others, producing one of the hardest substances on Earth. In graphite, carbon atoms form flat sheets held weakly together, making it soft enough for pencils. Other types of bonds. Metallic bond. For example, in copper, electrons flow freely, making metals shiny and conductive. Van der Waals or hydrogen bonds. Much weaker, important in holding sheets together as in graphite. So you have your tight bond with diamonds, and graphite has a van der Waals or hydrogen bond, which is weaker. That's why even though they're C, the same chemical composition, one is the hardest mineral on Earth and one is very soft mineral based on their atomic structure. Crystal lattices. The way atoms are bonded and arranged determines a mineral's properties. Diamond carbon is tetrahedral 3D lattice is ultra hard, whereas graphite carbon layers with weak bonds between them is so soft. Cleavage, hardness, and crystal shapes all come from their atomic order. Now, mineral groups. How do geologists make sense of the thousands of known minerals? By grouping them by their main chemical and ion. There are key groups. For example, you have oxides, an example is hematite. You have sulfides, an example is galena, PbS, and pyrite, FeS2. Then you have sulfates, which is gypsum, barite. Then you have halides, where you have your halite and you have your fluorite. You have carbonates, which is calcite and dolomite. You have phosphates, which is apatite, and silicates, we all know silicates, quartz, feldspar. And then you have your native ones that are gold, Au, diamond, C. The vast majority of Earth's crustal minerals are, you can guess, silicates. These are built of a unit called the silica tetrahedron, one silica in the middle, 4 oxygens at the corners, forming a 3D pyramid. Depending on how these tetrahedron join, isolated tetrahedron, for example, olivine, you have your single chain tetrahedron, which is pyroxene, double chain, which is amphibole, sheets is micas, clays, framework example is feldspar quartz, all corners of oxygen share. Solid solution is common in minerals like olivine, iron and magnesium can swap places because of the similar size and charge. Now, how do minerals form? Minerals form in several ways, but all require the right elements, the right conditions, and importantly, enough time. And where and how? From cooling magma, igneous rocks slowly cool and form large crystals. Fast cooling, there's tiny crystals or glass, and then basalt volcanic glass. So based on their cooling, so if minerals cool really quickly, then you can't see the crystals, and if the minerals cool over a long period of time, magma is cooling over a long period of time, you see that the crystals are really well developed. Sometimes you'll see quartz rock minerals where quartz is not fully hexagonal, but sometimes when you see a hexagonal quartz, that means it's taken its time and slowly developed. Now they also develop from cooling magma, we just spoke about that, from solutions. Dissolved ions crystallize as water evaporates or cools. Think salt flats or caves, paleothems. They can form from gas, rare, but some minerals form from volcanic gases. Through metamorphism, heat and pressure change minerals into new minerals inside existing rocks. And by weathering, some minerals break down or are altered at the surface. Like for example, organic processes, example calcite in shells and bones. These are all these biogenic minerals. Now mineral growth needs time. Quick processes is small crystals. Slow processes are large visible crystal grains. Mineraloids and exceptions. You always have exceptions in science. Opal is a mineraloid which lacks crystal structure. Pearl forms only via biology, so it's not a mineral by strict definition. Then we've studied about mineral properties in our previous lectures. We just recap it. A mineral's composition and structure control its hardness. So how can it scratch glass or a fingernail or nickels? Okay, so based on that you determine hardness of different minerals. Cleavage and fracture, how does it break? Based on the atomic structures, whether it's sheets, it's cube, it's conchoidal. The color of the mineral, the luster, the shine, whether it's metallic, dull, glassy, and what are the uses? Decorative, whether it's used for industrial, technological. Their abundance, rarity, and properties determine how we use them in everything from electronics to construction to art to health. Now, let's pull it all together. So we've had 2 lectures so far on minerals. We spoke about the physical properties, how do we identify them, how is a mineral formed. You can read more from your chapter 2 in minerals, but here's a little recap. Minerals are naturally occurring solids with specific composition and ordered atomic structures. Their physical properties arise from their chemical bonding and atomic structure. Most minerals fit into a handful of major groups. Silicates are by far the most abundant. They form in a range of environments from deep magma chambers to evaporating lakes to the shells of living creatures. Minerals resources are essential for everything from kitchen salt to your car to your smartphone. Next time you pick up a rock, look at your phone or shake salt on your fries. Remember, you're interacting with minerals, the hidden architecture of your world. That's it for this lecture, and you can now answer your lecture series questions. You can go through your quizzes, and then if you have any questions, I'm here on my Zoom during office hours, or if you want to email me on Canvas. I'll see you in the next lecture. Bye-bye.